practice make lots of different molecules. So this is actually, I had to pull this up from a long time ago. This is a very old slide. But these are all different structures that were created from a process of what we're going to talk about, diversity-oriented synthesis. So let me talk about the intellectual aspect of it. It was, the term was coined by Stuart Schreiber, my postdoctoral advisor, in 2000. And he compared it to, in this science paper, target-oriented synthesis. So we talked about natural product synthesis, and then he juxtaposed it, or he compared it to diversity-oriented synthesis, which is a different way of doing chemistry, a different reason for doing chemistry, to be honest with you. So, so this was the crowning paper, and it's a good paper for you guys to read. There was a question to come out of the final exam that may be out of this one. So it actually has evolved quite a bit from then, but it's good to read the historical nature of it. So let's talk about how molecules can be different from one another. There are three levels of diversity that I think we can think about. There's building block diversity, where you can think about making things and you can attach them to a core structure. And this is what combinatorial chemistry was, and why largely it failed, because these structures will always be benzodiazepines. They're not different structures. They just have different things attached to them. So the thing that I think diversity-oriented synthesis really called to the attention of chemists was that there's something called stereochemistry. So for the non-chemist in here, so these, look at this ring, they're all sp2 carbons, they're flat. So benzene is a flat structure, right? If you were to reduce all those double bonds in benzene, you would get cyclohexane, which would have a very different structure. It's three-dimensional, and it has two different points of attachment in three-dimensional space, somewhat represented by this. It's stereochemistry. So if the bond is black, it's coming out at you. If the bond is hashed, it's going out at the board. And so how we make those compounds represents how the molecule interacts with a three-dimensional structure in biology. So if that bond is coming forward or going in the back, that actually makes a difference in terms of how it's going to interact with its three-dimensional target. So how do we make that? Well, that's a whole different concept that we're not going to get into now, but that's a whole area of chemistry that chemists think about. Largely, most chemists don't care about how it's going to interact with biology. They just do it because they're good at doing it, and that's what they do. But those technologies have evolved to actually allow us to make these molecules. And this is an example. These are the L-hexoses, and this was a landmark synthesis in the 90s by Barry Sharpless and Masamune at MIT. That showed that we could generate all these different stereoisomers independently, and those are different compounds, and that those technologies evolved in order to do that. Now, the last level up, or the next level up, is skeletal diversity. And so this is how nature does DOS. In a sense, it's a very good example. You can take these two simple building blocks, and these two simple building blocks can give rise to these three structures. And it doesn't look like that would happen, but all it takes to generate these three structures is these two compounds and some enzymes. We'll call them polyketide synthases, and they interact in different ways, but they get together and they make these two compounds. And I always say, this one takes the largest number of steps to make relative to its left and right partners here. So this is an example of how if you start out with common building blocks, you can actually make lots of different types of structures. So this is sort of a key theme of DOS. So the next thing that I want to bring up is chemical efficiency. So remember, we use this as a common starting point for a natural product, what it looks like. This compound is a value. It takes 2 steps to synthesize it in the lab. So this is a drug-like compound. This compound takes about 25 chemical steps. This one takes 2. So the notion is, though, that we love the complexity of this one because we think that it helps us interact with different types of biological targets. It's specific. This one we can make tons of. So really what we're trying to do is merge the 2 concepts of making large numbers of compounds and the complexity of the compounds that we make. So that's what this is. So this is a compound I made in my postdoc many years ago. We never even published this, but what you'll notice about this compound is actually that it sort of fits the hybrid model of what we want to do. 3 chemical steps it took me to make this compound. So, but then you'll notice that its complexity is pretty impressive. It has 1, 2, 3, 5 different rings. As these stereo centers that we were talking about. It's not flat. So 3 steps, not 24. But then it has a lot of the features that this class of compound doesn't have. So this is an example of what we try to do with diversity-oriented synthesis. All right, so now I'm going to get to the evolution of DOS. And let me see where I'm at on time. Okay, we're good here. So how do we do that? That's the goal. That's the goal. Any questions up to now? No? You guys are quiet. It's a small group, so engage me with conversation, if you will. So let's talk about how the field evolved. So I'm going to go through a kind of timeline here that starts with that paper, which came out in 2000. Then I'm going to show you some things, and these are just to show you conceptually the chemistry, not to get involved in the reactions. I don't want you to think about what the reactions, but what the reactions are doing. So this is basically the timeline: complexity generation reactions, stereochemical diversification. Talk about selective synthesis, feature diversification. Then we end with this thing called Bill couple pair, which at least I hope my group knows about. I'll turn it over to you at that point. Okay, so let's talk about complexity generation, generating reaction. So in the beginning, like I said, molecules were generally very flat and very benzodiazepine looking, and that's what people were putting in compound collections. So this is a paper that was published in '98.